Tonight, on Cosmic Depths, I want you to stop thinking about the stars as beautiful lights in the sky and start thinking about them as real places, real suns, real systems, real distances. Because the moment you do that, one simple question becomes terrifying. If the closest star system to Earth is only next door in cosmic terms, then why does it still feel almost impossible to reach? The system we are talking about tonight is Alpha Centauri, the nearest stellar neighbour beyond our Sun, a name that sounds familiar, almost comforting, almost close. You may have heard it in documentaries, science books, space videos, and conversations about humanity's future among the stars. Alpha Centauri is often introduced as our nearest star system, about 4 light-years away. And when people say 4 light-years, it can sound small. 4 is a small number. 4 years is not a lifetime. 4 years ago feels recent. But in space, 4 light-years is not close the way your mind wants it to be close. 4 light-years is a wall. 4 light-years is an ocean without shore. 4 light-years is 25 trillion miles of darkness between us and the next possible destination beyond our solar system. When we say Alpha Centauri is close, we are speaking the language of the universe, not the language of human beings. For a galaxy that stretches across more than 100,000 light-years, 4 light-years is nearby. For a species whose bodies evolved to walk across fields, climb hills, cross rivers, and build cities on one small planet, 4 light-years is almost impossible to understand. It is close enough to tempt us, but far enough to humble us. It is near enough to make us dream, but distant enough to remind us that the universe was not built for our convenience. And that is the real story tonight. Alpha Centauri is not only a star system, it is a test of human ambition. It is the first great barrier between science fiction and reality. It is the place where our dream of becoming an interstellar species meets the cold mathematics of distance, speed, energy, time, and survival. Before we talk about reaching Alpha Centauri, we need to understand what Alpha Centauri actually is. Many people imagine it as one star, a single bright point sitting near our Sun in the cosmic neighbourhood. But Alpha Centauri is not one star. It is a system of 3 stars, tied together by gravity across enormous distances. 2 of them, Alpha Centauri A and Alpha Centauri B, form the main pair. They orbit each other in a slow, elegant gravitational dance that has been happening for billions of years. Far away from them, almost like a distant relative orbiting from the edge of the family, is Proxima Centauri, a small red dwarf star that is technically the closest known star to Earth after the Sun. Alpha Centauri A is the brightest member of the system. It is similar to our Sun in many ways. It is slightly more massive, slightly larger, and brighter. If you could replace our Sun with Alpha Centauri A, Earth would not instantly become an alien nightmare. The light would be stronger, temperatures might rise, the sun in the sky would feel more intense, but the basic nature of a stable star supporting a planetary system would remain familiar. That is part of why Alpha Centauri feels so emotionally powerful. It is not a monster star. It is not a dying giant, not a violent object, not a cosmic explosion waiting to happen. It is a star much like our own, shining nearby in the darkness, close enough to make us wonder whether worlds like Earth could exist around it. Alpha Centauri B is smaller and dimmer than Alpha Centauri A. It has less mass than our Sun and gives off less light. A planet orbiting Alpha Centauri B at the same distance Earth orbits the Sun would be colder. It would need to orbit closer to receive Earth-like warmth. But Alpha Centauri B is still a stable main sequence star. It burns hydrogen in its core, it shines steadily, it is old, reliable, and ordinary in the way stars can be ordinary. These 2 stars are separated by distances that change as they orbit each other. At their closest, they come within roughly the distance between the Sun and Saturn. At their farthest, they stretch apart beyond the distance from the Sun to Neptune. One full orbit takes just under 80 years. Think about that for a moment. Since the end of World War II, while humanity built nuclear weapons, sent satellites into orbit, walked on the moon, created the internet, mapped the human genome, built artificial intelligence, and watched the world transform again and again, Alpha Centauri A and B completed about one slow orbit around each other. Human history feels fast to us because we live inside it, but to stars, our entire civilization is just a flicker. The Alpha Centauri system was ancient before the first human city was built. It was ancient before agriculture. It was ancient before language took written form. It was ancient before Earth itself became a world of animals and forests. And it will still be there long after everything we know has changed. Now imagine a planet orbiting Alpha Centauri A. Stand on its surface during the night. The main star has set below the horizon, but the sky is not like Earth's sky. Somewhere above you, Alpha Centauri B shines with astonishing brightness. Not like a normal star, not like Sirius, not like Venus, not like the brightest object we see after the moon. At some points in its orbit, Alpha Centauri B could be bright enough to cast shadows. It might create a silver glow across the landscape, a second sun that does not bring full day, but refuses to let night become truly dark. Any life or civilization on such a world would grow up under a double-star sky. Their mythology, their calendars, their fears, their science, their sense of beauty would all be shaped by two suns, one for the day and one haunting the night. Then there is Proxima Centauri. Proxima is the closest star to our Sun, and yet it is nothing like the Sun. It is a red dwarf, small, cool, and dim. It has only a fraction of the Sun's mass and gives off only a tiny fraction of the Sun's light. If Proxima replaced our Sun, Earth would freeze. Oceans would become locked under ice. The warmth that makes our world alive would disappear. A planet orbiting Proxima would need to be extremely close to receive enough energy for liquid water. So close, in fact, that such a planet would probably become tidally locked, meaning one side would always face the star, while the other side remained in permanent darkness. Try to picture that kind of world. One half locked under endless red daylight, with Proxima hanging in the sky and never rising or setting. The other half trapped in eternal night, cold and dark, never seeing the star. Between the two hemispheres, there might be a ring of twilight, a permanent sunset zone where heat from the day side meets cold from the night side. If there is an atmosphere, winds might scream around the planet, carrying heat across the boundary between day and darkness. Clouds might form in strange patterns. Storms might become permanent. A world like that would not feel like Earth, but it might still be capable of something. Maybe chemistry, maybe oceans, maybe life, maybe nothing at all. Proxima Centauri orbits far from Alpha Centauri A and B. The distance is enormous, roughly 13,000 times the distance between Earth and the Sun. It is so far away from the central pair that one orbit takes hundreds of thousands of years. During one orbit of Proxima around Alpha Centauri A and B, entire human civilizations could rise, collapse, be forgotten, be rediscovered, and become mythology. A single orbit of that small red star is longer than the history of Homo sapiens in many cultural forms. That is the kind of timescale stars live inside, not years, not centuries, not even millennia. Stars live in millions, billions, and sometimes trillions of years. The Alpha Centauri system is estimated to be older than our Sun, around 5 to 6 billion years old. Our Sun is about 4.6 billion years old. This means Alpha Centauri was already shining before our solar system fully formed. before Earth had stable oceans, before life began in the seas, before the first cells, before oxygen filled the atmosphere, before animals crawled across land, before dinosaurs, before humans, before memory, before history. Alpha Centauri was already there. It was already moving through the galaxy with us. It was already part of the neighborhood. And long after our sun begins its final transformation, billions of years from now, Proxima Centauri may still be shining faintly. Red dwarfs burn their fuel so slowly that they may survive for trillions of years. There may be the last stars burning in the universe when all brighter stars have faded. This is why Alpha Centauri feels both close and ancient. It is our neighbor, but it belongs to a timescale far beyond us. It is nearby, but unreachable. It is familiar in some ways, but deeply alien in others. And the number that defines all of this is 4.24 light-years. That is the distance to Proxima Centauri. Alpha Centauri A and B are slightly farther away, about 4.37 light-years. In miles, that means roughly 25 trillion miles. 25 trillion miles to the nearest star beyond the Sun. This number is so large that the mind slides off it. We can write it down, we can repeat it, we can use it in calculations. But emotionally, we cannot hold it. Our brains were not built for trillion-mile distances. We understand walking distance, driving distance, the distance between countries, maybe even the distance to the moon. But 25 trillion miles is not a journey in the normal human sense. It is a gulf. For thousands of years, humans looked up at Alpha Centauri without knowing what it really was. Ancient people in the southern hemisphere saw it as a bright star in the constellation Centaurus. Sailors, observers, scholars, and skywatchers could see it, but to the naked eye, it appeared as one point of light. No one knew it was a multiple star system. No one knew it was our closest stellar neighbor. No one knew there might be planets there. The night sky held secrets quietly, as it always does, waiting for tools strong enough and minds patient enough to ask better questions. With the arrival of telescopes, the truth began to change. Observers eventually realized Alpha Centauri was not one star, but two close stars. This discovery mattered because binary stars are not just visual curiosities, they are gravitational laboratories. By watching two stars orbit each other, astronomers can calculate their masses and study how gravity works beyond the solar system. Over the centuries, astronomers carefully measured the changing positions of Alpha Centauri A and B. Slowly, year by year, they built a picture of the system's orbit. But for a long time, one major question remained unanswered. How far away was it? The answer came through parallax. Parallax is simple in concept, but extremely difficult in practice. Hold your finger in front of your face and look at it with one eye closed, then switch eyes. The finger appears to shift against the background. That happens because each eye sees from a slightly different position. Earth does something similar as it orbits the Sun. 6 months apart, Earth sits on opposite sides of its orbit. A nearby star should appear to shift slightly against the far background stars. That tiny apparent shift allows astronomers to calculate distance. But for stars, the shift is almost unbelievably small. Even for the nearest stars, it is less than 1 arcsecond, a tiny fraction of a degree. In the 19th century, astronomers finally began measuring stellar parallax successfully. Thomas Henderson, working from South Africa, studied Alpha Centauri carefully and detected its tiny shift. Around the same era, Friedrich Bessel measured parallax for another star, 61 Cygni, and published a confirmed distance. These measurements changed humanity's understanding of the universe. They proved that the stars were unimaginably far away. Not just higher lights, not just objects on a celestial sphere. They were suns, separated by enormous distances. Alpha Centauri, the nearest of all, was more than 4 light-years away. That discovery was one of the great intellectual shocks in human history. Before we measured stellar distances, the universe could still feel human-sized in imagination. After parallax, the sky became deep. The stars became remote. The heavens became physical and vast. For the first time, humanity had a ruler long enough to measure the true distance to another sun, and the answer was devastating. The closest star was 25 trillion miles away. 2 centuries later, after all our rockets, computers, satellites, space stations, Mars rovers, and deep space probes, we still have not reached it. Everything we know about Alpha Centauri comes from light. Light leaves those stars and travels for years through space before entering our telescopes. Those photons carry information. They tell us temperature, motion, chemical composition, brightness, stellar activity, and sometimes the presence of planets. We have never touched Alpha Centauri. We have never placed a probe in its system. We have never seen its planets up close. We have only studied the light that arrives after a 4-year journey through the void. Astronomy is powerful because it lets us learn from across impossible distances, but it also reminds us of our limits. Knowing about a place is not the same as reaching it. When you look at Alpha Centauri, you are not seeing it as it is right now. You are seeing it as it was more than 4 years ago. If Proxima Centauri experienced a powerful flare tonight, we would not know immediately. The information would travel outward at the speed of light, crossing space for 4.24 years before reaching us. Until then, we would continue seeing the old light. This is true of every star. The universe we see is delayed. The night sky is not live. It is a collection of ancient messages arriving at different times from different distances. Some stars show us light from decades ago, others from centuries ago. Galaxies show us light from millions or billions of years ago. Alpha Centauri is close enough that the delay is only a few years, but the principle is the same. Distance separates us not only in space, but in time. This time delay creates a strange kind of loneliness. If there were intelligent beings around Alpha Centauri and we sent them a message tonight, it would take more than 4 years to arrive. If they answered immediately, their reply would take more than 4 years to return. One question and one answer would take almost 8.5 years. That is not conversation as human beings understand conversation. It is correspondence across time. You might ask a question as one version of yourself and receive the answer as another version years later. Your life may have changed. Your society may have changed. The people who sent the message may be older, gone, or no longer interested. Even communication with the nearest possible neighbours would be slow, delayed, and emotionally strange. And travel is far worse. Light can cross the distance in a little more than 4 years, because light is the fastest thing in the universe. Nothing with mass can travel at light speed. A spacecraft can move fast, but it cannot move like light. The fastest human-made spacecraft so far, the Parker Solar Probe, reaches incredible speeds by falling close to the Sun and using the Sun's gravity. It can move around 430,000 miles per hour. On Earth, that is almost unimaginable speed. It could cross continents in moments. It could reach the moon quickly compared with any normal vehicle. But compared with interstellar distances, it is still slow. If Parker Solar Probe were aimed toward Proxima Centauri and could maintain that kind of speed, it would still take thousands of years to arrive. This is where the dream begins to crack. We are used to thinking of technological progress as something that turns impossible journeys into possible ones. The ocean once seemed vast, but ships crossed it. The sky once seemed unreachable, but aircraft crossed it. Space once seemed unreachable, but rockets reached it. The moon once seemed impossible, but humans walked there, so naturally we imagine the stars are the next step. But Alpha Centauri is not just the next step. It is a step across a distance so large that the fastest machines we have ever built become almost motionless in comparison. The Voyager spacecraft are perfect examples. Voyager 1 and Voyager 2 are among humanity's greatest achievements. Launched in 1977, they explored the outer planets and then continued outward. Voyager 1 is now the farthest human-made object from Earth. It has crossed beyond the main influence of the solar wind and entered interstellar space. That sounds like we have begun interstellar exploration, but in reality, Voyager has barely left the front porch. It is light hours away, not light years away. Alpha Centauri is thousands of times farther. If Voyager were aimed at Alpha Centauri, it would take tens of thousands of years to get there. 75,000 years is a number that should make you quiet. 75,000 years ago, modern humans existed, but civilization did not. There was no writing, no agriculture, no cities, no governments, no mathematics, no astronomy, no telescopes, no engines, no electricity, no internet, no rockets. Almost everything we think of as human civilization has happened in less time than Voyager would need to reach the nearest star. And Voyager is not aimed at Alpha Centauri. It will never go there. It will drift through the galaxy in another direction, carrying its golden record as a silent memory of Earth. This means our current spacecraft are not just a little too slow, they are too slow by the scale of history itself. To reach Alpha Centauri in a meaningful time, we would need to move at a significant fraction of the speed of light. 1% of light speed would already be a revolution. At 1% light speed, the journey would take about 424 years. 4 centuries is far better than 75,000 years, but it is still longer than the lifespan of any human being, and longer than the existence of many modern nations. A mission launched today would arrive in a world so far in the future that our current civilization would be ancient history. A spacecraft travelling at 1% light speed might work for a robotic probe if it could survive long enough, but a human mission at that speed would require a generation ship. A generation ship is not simply a big rocket, it is a complete society inside a spacecraft. People would be born on it, live on it, have children on it, grow old on it, and die on it before the destination ever came near. The people who finally arrived at Alpha Centauri would not be the people who left Earth. They would be descendants. They would inherit a mission they did not choose. They would arrive at a star selected by ancestors they never met. At first, this idea sounds majestic. A ship carrying humanity across the stars. A moving world, a bridge between suns. But when you think about the human reality, the idea becomes heavy. Is it right to choose the lives of unborn generations? Is it right to create children inside a spacecraft, knowing they will never see Earth, never walk under an open sky, never smell rain, never swim in an ocean, never feel wind from a natural horizon? What happens when they grow up and ask why their lives were shaped by a decision made centuries before their birth? What happens if they no longer want the mission? What happens if they want to turn back, but turning back is impossible? A generation ship must solve mechanical problems and human problems at the same time. Mechanically, it needs power systems, propulsion, life support, radiation shielding, water recycling, air recycling, food production, medical care, manufacturing, spare parts, and navigation. These systems must last not for weeks or years, but for centuries. Machines break, electronics degrade, materials fatigue, micrometeorites strike, radiation damages circuits, life support systems clog, corrode, and fail. Every essential system needs backups, and the backups need backups. The ship must be able to repair itself, because no supply ship is coming. But the human problems may be even harder. A generation ship is a closed society. It needs laws, education, leadership, conflict resolution, culture, purpose, and continuity. It needs people to maintain knowledge across generations. It needs children to learn engineering, medicine, agriculture, mathematics, history, and the mission itself. It needs social stability. It needs trust. It needs enough freedom to remain human, but enough discipline to survive. A single act of sabotage could kill everyone. A political crisis could fracture the ship. A disease outbreak could become catastrophic. A breakdown in education could mean future generations no longer understand how to maintain the systems keeping them alive. On Earth, civilizations rise and fall even with open land, abundant resources, millions of people, and room to recover. On a generation ship, the margin for failure is much smaller. There is nowhere to escape. No neighboring country, no wilderness, no second city, no ocean to cross. The ship is the world. If the ship's society collapses, the mission collapses. If the mission collapses, everyone dies or drifts forever. This is why interstellar travel is not only a technological challenge, it is a civilizational challenge. You do not just build engines, you build a culture strong enough to survive centuries of confinement. Suppose instead we travel faster. At 10% of the speed of light, Alpha Centauri could be reached in about 42 years. That sounds much better. A person could leave Earth as a young adult and arrive as an older adult. The same generation that launches could see the destination. But 10% light speed is far beyond our current spacecraft, and at that velocity, the universe becomes dangerous in ways that are difficult to imagine. A tiny grain of dust hitting the front of the spacecraft would release enormous energy. At ordinary speeds, dust is a hazard. At relativistic speeds, dust becomes a weapon. Interstellar space is emptier than any vacuum we can create on Earth, but it is not perfectly empty. There are atoms, gas, dust, charged particles, and cosmic rays. Over 25 trillion miles, a spacecraft traveling at extreme speed will encounter material. Even individual atoms strike with more energy when the spacecraft is moving fast enough. Dust grains can damage or destroy instruments. Larger particles could be catastrophic. The ship would need shielding, possibly thick physical shielding, electromagnetic fields, sacrificial layers, or some kind of protective cloud ahead of the craft. But every shield adds mass. Every kilogram of mass requires more energy to accelerate. More energy means more fuel or more powerful propulsion. More fuel means more mass. The problem grows. This is the tyranny of the rocket equation. Rockets must carry propellant, but propellant has mass, and you need propellant to accelerate the propellant. As speed requirements increase, the amount of fuel needed grows brutally. Chemical rockets, the kind that launched humanity into space, are excellent for reaching orbit and traveling within the solar system, but they are not enough for interstellar travel at meaningful speeds. You cannot simply build a bigger chemical rocket and go to Alpha Centauri. The fuel requirements become absurd. To reach a significant fraction of light speed, we need propulsion methods far beyond ordinary rockets. Nuclear pulse propulsion is one idea. A spacecraft could use repeated nuclear explosions behind a massive pusher plate, riding the shockwaves forward. In principle, this could produce much higher speeds than chemical rockets, but the political and safety problems are enormous. Detonating nuclear devices in space raises treaties, dangers, public fear, and moral concerns. Even if the physics works, civilization may not be willing to accept the risks. Fusion propulsion is another possibility. Fusion powers the stars. If we could build a spacecraft engine that fuses light elements and directs the energy into thrust, we could achieve far greater speeds. But useful fusion power is still one of humanity's hardest engineering challenges. We have made progress on Earth, but a compact, reliable, long-lasting fusion engine for a spacecraft is far beyond what we currently have. A fusion starship remains possible in theory, But theory is not the same as an engine bolted to a vehicle. Antimatter propulsion is even more extreme. Matter and antimatter annihilate when they meet, converting mass into energy with extraordinary efficiency. In theory, antimatter is one of the most powerful fuels imaginable. In practice, we can produce only tiny amounts at enormous cost. Storing antimatter is terrifyingly difficult because it cannot touch normal matter. It must be contained by magnetic fields with near-perfect reliability. The amount needed for an interstellar mission would be vastly beyond what we can produce today. Antimatter feels like a key to the stars, but for now it is a key we cannot afford, cannot manufacture in useful quantities, and cannot safely carry. Laser sails may be more realistic for small probes. Instead of carrying fuel, a spacecraft could unfold a thin reflective sail and be pushed by powerful lasers from Earth or orbit. Light has momentum, and a sufficiently powerful beam can push a very light sail to extreme speeds. This is the basic idea behind breakthrough starshot. Tiny probes, perhaps weighing only grams, could be attached to sails and accelerated to 20% of light speed. At that speed, they could reach Alpha Centauri in about 20 years. This is one of the few concepts that could send something to another star within a human lifetime. But even laser sails face enormous problems. The laser array would need to be incredibly powerful, perhaps requiring energy on the scale of major power plants. The lasers would need to stay precisely focused on a tiny sail as it accelerates away. The sail would need to be ultra-light, extremely reflective, and strong enough not to tear or vaporize under intense laser pressure. The tiny spacecraft would need cameras, sensors, a computer, power, communication, and navigation systems packed into a mass of only grams. It would need to survive decades in deep space, endure radiation and dust impacts, wake up near Alpha Centauri, collect data during a brief flyby, and transmit that data back across 25 trillion miles. Every part of this is difficult. And even if it works, the probe cannot easily stop. The laser that pushed it is back near Earth. There is no matching laser at Alpha Centauri to slow it down. The probe would flash through the system at a fraction of light speed, take measurements as quickly as possible, and continue into interstellar darkness. After decades of travel, the encounter might last hours, maybe days. That is the strange reality of the most realistic near-future interstellar missions. They do not arrive like explorers settling into orbit. They pass like bullets through a distant system, taking pictures as they go. To truly explore Alpha Centauri, a spacecraft would need to decelerate. It would need to slow down enough to enter orbit around a star or planet. But slowing down requires energy. If you accelerate to 10 or 20% light speed, you must remove that velocity at the destination. That means carrying braking fuel, which must itself be accelerated from the start. This doubles or multiplies the difficulty. Some concepts involve magnetic sails that interact with stellar wind, or light sails that use radiation from the destination star, or aerobraking through a planet's atmosphere. But all of these depend on conditions and technologies we do not yet control. A flyby is easier because it avoids braking, but a flyby is incomplete. This is the heartbreak of Alpha Centauri. The easiest mission is still incredibly hard, and the scientifically satisfying mission is much harder. A tiny flyby probe might give us images and measurements. An orbiter would require far more energy and complexity. A lander would be harder still. A human mission would be almost beyond comprehension. And all of this for the nearest star. Not the 10th nearest, not the galactic center, not another galaxy. The nearest. This should change how we think about space. The stars in the night sky look close because they are projected onto the same darkness. Constellations trick the eye into seeing patterns, shapes, and neighborhoods. But the stars are not painted on a ceiling. They are scattered through three-dimensional space at enormous distances. Some stars that appear close together in the sky are nowhere near each other in reality. One may be tens of light years away, another hundreds. The sky flattens depth into beauty. Astronomy restores the depth, and the depth is terrifying. Alpha Centauri is truly close by cosmic standards. That is why it matters. If we cannot reach the closest star, then the rest of the galaxy becomes almost unimaginable. Sirius is more than twice as far away. Vega is many times farther. The center of the Milky Way is tens of thousands of light years away. Andromeda is millions of light years away. We talk about galaxies as if they are objects in a picture, but they are distances so vast that even light needs millions of years to cross them. If Alpha Centauri is a wall, the galaxy is an endless continent beyond that wall. So at the end of this first part, we are left with a strange truth. Alpha Centauri is our nearest neighbor, but it is not close in any human sense. It is a triple star system filled with beauty, possibility, and mystery. It may contain worlds worth studying. It may hold answers about planets, red dwarfs, habitability, and perhaps life. But the distance between us and that system is so enormous that every dream of reaching it becomes a struggle against the deepest laws of physics. We can see it, we can study it, we can calculate it. But reaching it is something else entirely. And once you understand that, the next question becomes even more serious. If we ever try to send human beings across that distance, what would it do to them, to us, and to the future of humanity itself? Now imagine that humanity decides machines are not enough. Imagine that one day, after centuries of technological progress, governments, scientists, private companies, and dreamers agree on something enormous. We will not only observe Alpha Centauri, we will not only send tiny probes, we will send people, real human beings, a crew, families perhaps, a living mission, a piece of Earth sealed inside a spacecraft and sent across the space between stars. At first, the idea sounds heroic, the first humans to leave the solar system forever, the first people to cross interstellar space, the first ambassadors of Earth to another star. But the moment you slow down and truly think about what that journey means, the romance becomes heavy. Because a human mission to Alpha Centauri would not be like Apollo, it would not be like Mars, it would not even be like the first ocean crossings. It would be a permanent separation from everything human beings have ever known. The moon is close. It is about 240,000 miles away. Light crosses that distance in just over 1 second. Apollo astronauts could speak with Earth almost in real time. Their journey took days. Mars is much farther, but still within the solar system. Depending on the positions of the planets, radio messages take minutes to travel between Earth and Mars. A Mars crew would experience delay, isolation, danger, and distance, but Earth would still be present. Mission control would still matter. Families would still be able to send messages within a meaningful time frame. Rescue would be difficult, perhaps impossible in some situations, but the mission would still belong to the solar system. Alpha Centauri is different. A message from Alpha Centauri takes more than 4 years to reach Earth. A reply takes more than 4 years to return. If a human crew reached Alpha Centauri and sent a message saying, "We have arrived," Earth would celebrate that arrival more than 4 years after it happened. If Earth responded immediately, the crew would hear the congratulations more than 8 years after they arrived. That means no real-time conversation, no quick advice, no emergency support, no emotional closeness in the ordinary sense. Communication becomes a slow exchange of memories. Messages become time capsules. A person does not speak to the present, they speak to the future. During the journey, the delay grows gradually. In the early months, communication with Earth may still feel manageable. Signals take hours, then days, then weeks. But as the ship moves farther away, Earth becomes less of a partner and more of an archive. After the ship is 1 light year away, a message takes 1 year to reach Earth and another year for the reply to return. A simple question takes 2 years to answer. After the ship is halfway to Alpha Centauri, the round-trip delay is more than 4 years. By then, if something goes wrong on board, Earth cannot solve it in time. The crew must handle everything themselves: medical emergencies, technical failures, psychological crises, political disputes, navigation errors, life support problems, births, deaths, accidents, and disasters all become local problems. The ship is on its own. This is where interstellar travel becomes a social experiment on a scale never attempted. A human starship would not be only an engineering project, it would be a society. Even if the journey lasted only 40 years, the crew would need a functioning community. They would need leadership, trust, rules, routines, conflict resolution, education, medical care, mental health support, and a shared sense of purpose. They would need to survive not only the emptiness outside, but the pressure inside. The same people, the same rooms, the same machinery, the same artificial environment, year after year after year. No natural weather, no open fields, no forests, no city streets, no new horizon, just the ship. A 40-year journey at 10% light speed might seem possible because it fits inside a human lifetime. But psychologically, 40 years in deep space is still almost unimaginable. A young person could leave Earth in their 20s and arrive near retirement age. Their parents might die while they are in flight. Their friends on Earth would age and change. Political systems might shift. Cities might transform. Technologies might become obsolete. The culture they left behind would not remain frozen. Earth would continue without them. By the time they arrived, the world that launched them would be gone in a cultural sense. They would be people from a past era arriving at a future star. Inside the spacecraft, time would behave differently emotionally. The ship would move at a tremendous speed, but the crew might feel trapped in stillness. There would be no landscape rushing past, no road, no ocean waves, no clouds below. Outside the windows, the stars would barely change day by day. Earth would fade behind them, slowly becoming just another point of light. Alpha Centauri would grow brighter ahead, but so slowly that the human eye might not notice except over months or years. The crew would be traveling faster than any humans in history, yet daily life would feel repetitive, enclosed, and suspended. That contradiction could wear on the mind. Human beings need change. We need rhythm. We need seasons, weather, distance, privacy, novelty, and the ability to leave one environment and enter another. On Earth, even ordinary life gives us countless sensory changes. Morning light, evening shadows, different rooms, different streets, different people, different smells, different sounds, rain, heat, wind, dust, traffic, animals, trees, sky. A starship replaces all of that with controlled systems. Air is recycled, water is recycled, food is grown or manufactured in controlled environments. Light is artificial, gravity may be artificial. The sky is a window into darkness. The body may survive, but the mind has to adapt to a world made entirely by machines. We have hints from submarines, Antarctic research stations, space stations, and isolation experiments, but no true comparison. Astronauts on the International Space Station live in confinement, but they are close to Earth. They can speak with family. They see Earth below them every 90 minutes. Their missions last months, not decades. Antarctic crews face isolation, but Earth is still outside the door. Submariners live sealed away, but they eventually return to the surface. An interstellar crew would have none of that. There is no surface. There is no outside environment compatible with human life. There is no rescue. The ship is the only habitable reality for light years in every direction. Now imagine a generation ship. This is the slower, but perhaps more realistic human version. If the ship travels at 1% light speed, the journey takes more than 4 centuries. No one who leaves Earth will arrive. Their children will not arrive. Their grandchildren may not arrive. The destination belongs to descendants many generations removed from the original crew. The ship must sustain a population long enough for birth, childhood, adulthood, aging, death, and cultural transmission to repeat many times. It must become a moving world with its own history. The first generation may be volunteers. They may believe in the mission. They may accept that they will die in space. They may see themselves as founders, pioneers, the first people to carry life toward another star. But the second generation is different. They are born on board. They did not sign a contract. They did not choose to leave Earth. They inherit the walls, rules, risks, and destination. The third generation is even further removed. Earth becomes a story. The fourth generation may know Earth only through videos and lessons. By the 10th generation, Earth could become mythic. The ancestral planet, the lost garden, the origin world. May be loved, may be resented, may be politically useful, may be spiritually transformed. This is one of the most powerful and unsettling consequences of generation travel. Culture does not remain static. Language changes, beliefs change, customs change, priorities change. The mission itself may change meaning. The original documents may be preserved, but interpretation evolves. Some people may see the destination as sacred duty. Others may see it as a prison sentence imposed by dead ancestors. Some may want to maintain strict control to ensure survival. Others may demand freedom. Some may believe the ship should continue. Others may want to slow down, turn aside, or create a permanent life in space. The mission could become a political struggle. On Earth, societies can expand, migrate, trade, and absorb shocks. On a generation ship, everything is limited. Population size must be controlled. Resources must be managed. Waste must be recycled. Energy must be conserved. Food production must be reliable. Education must be maintained. Genetic diversity must be protected. Health must be monitored. Even reproduction becomes a mission-critical issue. Who is allowed to have children? How many? Under what conditions? What happens if too many children are born? What happens if too few are born? These are deeply personal human questions, but on a generation ship, they become survival calculations. The ship also needs governance. Democracy sounds ideal, but what happens if voters choose policies that endanger long-term survival? Authoritarian control might preserve systems, but what happens if leadership becomes corrupt? A council of experts might make rational decisions, but what happens when people resent being ruled by technicians? A religious or cultural system might preserve unity, but what happens if it rejects necessary science? There is no simple solution. A starship society must balance freedom and survival in a way no society on Earth has ever had to do permanently. Knowledge preservation is another challenge. The ship depends on advanced technology. Its people must understand life support systems, propulsion systems, navigation, radiation shielding, agriculture, medicine, manufacturing, computing, and materials repair. But over centuries, knowledge can degrade, training systems can fail, education can become ritual instead of understanding. A generation might know which buttons to press without understanding why. If a rare system fails after 200 years, will anyone know how to repair it? Will the tools exist? Will the necessary materials still be available? Will the knowledge be preserved in usable form? A ship can die not only from an explosion, but from forgetting. Then there is the environment outside the ship. Interstellar space is dark, cold, and thin, but not harmless. Cosmic rays constantly pass through space. High-energy particles can damage electronics and living tissue. A human crew needs shielding. Water, hydrogen-rich materials, thick hulls, and magnetic fields might help, but shielding adds mass and complexity. Micrometeorites and dust grains also threaten the ship, especially at high speed. The vessel must survive impacts, radiation, system degradation, and the constant stress of operating far from any repair facility. It must be both spacecraft and planet, machine and home. If the ship finally reaches Alpha Centauri after centuries, the people on board may no longer feel like Earth people. They may be biologically human, but culturally separate. Their accents, languages, beliefs, politics, and identity may have evolved. They may have never felt natural gravity if the ship used rotation. They may have never seen a horizon. They may have no emotional connection to animals, oceans, forests, or weather. For them, Earth might not be home. The ship is home. The destination is destiny. Earth is origin, but not memory. And what if Alpha Centauri is disappointing? What if Proxima b has no atmosphere? What if it is blasted by radiation? What if there are no habitable planets around Alpha Centauri A or B? What if the system is scientifically fascinating, but useless for settlement? The ship arrives after centuries and finds no new Earth. Then what? Return is impossible. Continuing to another star might take centuries more. Staying in orbit or building habitats may be possible if the ship has enough capability, but that means the journey never truly ends. The colonists may discover that they did not travel to a home. They traveled to another place where survival still depends on machines. That possibility is why robotic exploration must come first. Before sending people, humanity would need to know far more about the system. We need better telescopes, better planet detection, better atmospheric analysis. Perhaps one day, small interstellar probes that can fly through the system and return data. We need to know whether Proxima b has an atmosphere, whether it has water, whether radiation conditions are survivable, whether there are planets around Alpha Centauri A and B, whether there are asteroids or resources, whether stable habitats could be built. Sending humans blindly would be reckless beyond imagination. Proxima b is the object that makes all of this feel urgent. Discovered in 2016, it is the closest known potentially habitable exoplanet. It orbits Proxima Centauri every 11.2 days. It is at least somewhat more massive than Earth. Because Proxima is small and dim, the habitable zone lies close to the star, and Proxima b sits in that region where liquid water could exist under the right conditions. That phrase must be repeated. Under the right conditions. Habitability is not guaranteed. Being in the habitable zone does not mean a planet is alive. It does not even mean it has water. It only means that if other factors are favourable, liquid water could exist. Proxima b may be tidally locked. One side may face eternal daylight, the other eternal night. If it has an atmosphere, heat could circulate between the hemispheres. If the atmosphere is thick enough, the climate might be stable in some regions. If there is water, perhaps oceans or ice sheets could exist. Maybe the twilight zone between day and night could support mild conditions. But Proxima is an active red dwarf. It produces flares. These flares can unleash radiation and charged particles that may strip away atmospheres over time. A close-in planet without a strong magnetic field could be exposed and barren. Proxima b might be one of the most important planets ever discovered, or it might be a dead rock. We do not know because we cannot yet see it clearly. We detected Proxima b indirectly by watching Proxima wobble due to the planet's gravity. That wobble tells us a planet is there. It gives us minimum mass and orbital period. But it does not give us a photograph. It does not reveal oceans, clouds, continents, ice, or life. We do not know the colour of its sky. We do not know if it has weather. We do not know if it has volcanoes, magnetic fields, or an atmosphere. We do not know whether microbes exist beneath its surface or in its oceans. It is both known and unknown, a real world hidden behind distance. If life were found on Proxima b, even simple microbial life, the meaning would be enormous. Life would no longer be an Earth-only phenomenon. If life arose independently on Earth and around the nearest star, then life might be common throughout the galaxy. The universe would feel different. Not necessarily friendly, not necessarily crowded with civilizations, but biologically active, alive in many places. But if Proxima b is sterile, that matters too. It may teach us that red dwarf planets are hostile, that flares are destructive, that atmospheres are fragile, that Earth-like conditions are rarer than we hope. Either answer would change science. This is why Breakthrough Starshot captured so much imagination. A tiny probe travelling at a fraction of light speed could reach Alpha Centauri in about 20 years. It might fly past Proxima, point instruments at Proxima b, and send data back. The images might be crude, but even a few pixels from a planet around another star would be historic. A spectrum of its atmosphere would be even more valuable. If we detected oxygen, methane, water vapor, or chemical disequilibrium, scientists would debate the possibility of life for generations. If we detected no atmosphere, we would learn something equally important. The first interstellar probe may not answer everything, but it would begin a new era. Yet the mission would be unbelievably hard. A gram-scale probe must survive acceleration from powerful lasers. It must survive 20 years in space. It must carry enough capability to gather useful science. It must transmit data back to Earth. And because so many things can go wrong, the mission may need to send hundreds or thousands of probes, hoping some survive. This is not a majestic starship. It is more like scattering seeds into a cosmic storm and hoping a few reach the soil. But perhaps that is how interstellar exploration begins, not with giant ships, but with tiny scouts. There were earlier, grander visions. Project Daedalus in the 1970s imagined a huge fusion-powered spacecraft weighing tens of thousands of tons, designed to fly to another star in decades. It would use fusion reactions involving deuterium and helium-3, producing thrust through repeated fusion pulses. The design was serious, based on known physics, but it required technology and infrastructure humanity still does not have. Helium-3 is rare on Earth. A Daedalus-like mission might require mining the moon or the atmospheres of gas giants. It would require large-scale space industry, orbital construction, fusion control, and enormous investment. Project Icarus later updated the concept, but the central lesson remained. Interstellar travel is possible in physics, only if civilization becomes far more capable than it is today. That may be the real barrier. Not only speed, not only distance, not only engines, civilization itself. Can humanity cooperate for a project that may take decades before results arrive? Can nations invest in something whose reward may come after current leaders are gone? Can the public remain interested during years of silence? Can science survive political shifts? Can we build for future generations rather than immediate profit? An interstellar mission asks us to become patient, and patience may be harder than propulsion. At the same time, we must face the ethical question of cost. Why spend billions or trillions trying to reach Alpha Centauri when Earth has urgent problems? Climate change, poverty, disease, war, inequality, food insecurity, water shortages, and environmental collapse are not imaginary. They are here. Some people will argue that money should be spent solving problems on Earth. Others will argue that exploration is part of what makes humanity human, that great scientific missions inspire technology, cooperation, and meaning. Both sides contain truth. The mistake is treating space exploration as an escape from Earth. Alpha Centauri cannot save us from our responsibilities here. This is one of the most important lessons in the entire story. Alpha Centauri is not a backup plan. Proxima b, even if promising, is not an emergency shelter for humanity. It is too far away. No fleet of ships can evacuate billions of people across 4 light years. No crisis on Earth can be solved by moving to another star. Mars is close compared with Alpha Centauri, and Mars is still incredibly difficult. The Moon is close, and permanent life there remains a challenge. Another star system is not a practical refuge. It is a scientific frontier. If Earth becomes unlivable, Alpha Centauri will not rescue us. That makes Earth more precious, not less. Every breath we take depends on this atmosphere. Every crop depends on this soil, this water, this climate. Every human story happened here. Every language, every song, every friendship, every city, every invention, every telescope, every rocket, every dream of another star began on Earth. We should explore the universe, but not because we believe Earth can be discarded. We should explore because curiosity matters, knowledge matters, and understanding our place in the cosmos matters. But Earth remains the only known world where human life is naturally possible. Now we must widen the lens. Alpha Centauri may help explain the Fermi paradox. If the galaxy has hundreds of billions of stars and many planets, where is everyone? Why have we not detected alien civilizations? Why have we not seen probes, signals, or unmistakable evidence of technological life? There are many possible answers. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves. Maybe they do not communicate in ways we understand. But Alpha Centauri suggests another possibility. Maybe the stars are simply too far apart. Every civilization faces the same physics. The speed of light is not a human limitation. It applies everywhere. The rocket equation is not our private problem. It applies to all matter. Dust impacts, radiation, energy requirements, and communication delays affect any spacecraft built by any species. Maybe many civilizations look up, calculate the distances, dream of the stars, and realize how hard crossing the void truly is. Maybe the galaxy is not empty. Maybe it is full of isolated islands, each civilization trapped around its own star, listening across the darkness, wondering why no one answers. This would be a lonely universe, but a realistic one. Science fiction gives us galactic empires, faster than light ships, instant communication, starports, alien trade routes, and wars across the stars. Real physics may give us something colder, civilizations separated by years, centuries, and millennia of travel time. No empire can govern effectively across light years with long communication delays. No trade network makes sense if shipping takes decades or centuries. No war fleet can respond quickly. No ambassador can hold a normal conversation when replies take years. The universe may not allow cosmic civilization in the way we imagine it. If that is true, Alpha Centauri is not just a destination. It is the first wall of a cosmic prison. A beautiful wall, shining in the southern sky, but a wall nonetheless. It tells us that the stars are visible, measurable, and perhaps even understandable, but not easily reachable. We may be able to send probes, maybe one day small groups of humans, maybe after centuries, colonies. But the dream of quickly spreading across the galaxy may remain fantasy. Not because we lack courage, but because space is too large and light is too slow. And yet, there is beauty in this limitation. The universe is not small, it is not convenient, it is not designed around us. That truth humbles us, but it also gives meaning to what we are able to do. We are tiny beings on one planet, but we can measure the distance to Alpha Centauri. We can study stars from light years away. We can detect planets we cannot see. We can calculate trajectories for missions that may not launch for generations. We can imagine worlds under red suns and double star skies. We can ask whether life exists beyond Earth. The universe may be vast and indifferent, but we are conscious within it. That consciousness matters. Maybe one day a tiny spacecraft from Earth will cross the distance. Maybe it will carry no human body, only instruments. Maybe it will be pushed by lasers, accelerated beyond anything we have ever built. It will pass through darkness for 20 years, silent and small, a fragile messenger from a fragile world. Then, near Proxima Centauri, it will wake fully, turn its sensors toward a planet, and collect data. It will not stop. It will not land. It will not return. It will simply look, remember, and transmit. More than 4 years later, Earth will receive the whisper. Imagine the first image. Not an artist's rendering, not a simulation, a real image from another star system. Maybe Proxima b is a dark, barren rock. Maybe it has clouds. Maybe it has ice. Maybe it has an atmosphere glowing under red light. Maybe the image is blurry, maybe only a few pixels. But those pixels would come from another star. Humanity would look at them and know that something we built crossed the gulf. The nearest star would no longer be only observed from afar, it would have been visited, however briefly, by a machine from Earth. That moment would not make us masters of the galaxy. It would not solve interstellar travel. It would not create a colony. It would not save Earth. But it would change the meaning of the impossible. It would prove that the gulf can be crossed by at least something. And once one probe reaches Alpha Centauri, future generations may build better ones, larger probes, slower probes that can brake, orbiters, landers. Perhaps one day, after centuries of patience, human missions. Progress may be slow, but history often begins with small steps that look inadequate at first. For now, though, we remain here, on Earth, under one sun, with one moon, inside one solar system. Our telescopes reach farther than our bodies. Our imagination travels faster than our machines. We can see Alpha Centauri, but we cannot touch it. We can dream of Proxima b, but we cannot stand on it. We can calculate starship trajectories, but we cannot yet build the civilization needed to send them. This is not failure, it is perspective. It tells us where we are in the story. We are not yet an interstellar species. We are a planetary species, beginning to understand the size of the cage. And maybe that understanding is the first real step. Before we cross the stars, we must stop underestimating them. Before we build starships, we must understand what distance means. Before we dream of escaping Earth, we must learn to protect Earth. Before we imagine colonies under other suns, we must become wise enough to survive under this one. Alpha Centauri does not tell us to give up, it tells us to grow up. It tells us that the universe is vast, that dreams require discipline, and that exploration without humility becomes fantasy. So as we move toward the final part of this journey, the question is no longer only whether Alpha Centauri can be reached, the question becomes deeper. If the nearest star is this hard to reach, what does that mean for humanity's place in the universe? Are we future explorers, destined to spread outward, slowly and painfully, one star at a time? Or are we cosmic castaways, able to see distant shores, but never truly reach them? And if Earth may be the only world we can ever fully call home, then what responsibility does that place on us right now? That is where the final part begins. Now, as we reach the final part of this journey on cosmic depths, we have to face the most uncomfortable truth in the entire story. Alpha Centauri is not terrifying because it is some distant, mysterious object at the edge of the galaxy. It is terrifying because it is the closest star system to us. It is the next star over. It is the first possible destination beyond our sun. And if the closest star is already this difficult to reach, then the rest of the galaxy becomes something almost beyond imagination. Alpha Centauri is not the hardest target in the Milky Way. It is the easiest one. It is the nearest door. It is the first step. And that first step alone may require technology, patience, energy, cooperation, and courage far beyond anything humanity has ever demonstrated. When people dream about humanity spreading among the stars, they often imagine the galaxy like a vast ocean waiting for ships. They imagine one world leading to another, one colony leading to another, one generation pushing deeper and deeper into space until human civilization expands across the Milky Way. It is a beautiful idea. It is powerful. It gives our future a sense of destiny. But Alpha Centauri forces us to slow down and ask a harder question. What if the stars are not an open ocean? What if they are distant islands, separated by waters so wide that almost no one can cross them? What if the dream of a galactic civilization is not impossible in theory, but so difficult in practice that it may never happen the way we imagine? The nearest star system is about 4.24 light-years away. Sirius is about 8.6 light-years away. That is already more than twice as far. Epsilon Erigani is about 10.5 light-years away. Tau Ceti is about 12 light-years away. Vega is about 25 light-years away. These are still considered nearby stars in cosmic terms, but for us, they are separated by distances that would make Alpha Centauri look almost easy. And then beyond the local neighborhood, the numbers explode. The center of the Milky Way is about 26,000 light-years away. The galaxy itself is more than 100,000 light-years across. Andromeda, the nearest large galaxy, is around 2.5 million light-years away. These numbers are not distances in any human sense. They are cosmic barriers. If a spacecraft traveling at 10% of the speed of light takes more than 40 years to reach Alpha Centauri, then reaching a star 25 light-years away would take around 2.5 centuries at that same speed. Reaching the galactic center would take hundreds of thousands of years. Reaching Andromeda would take tens of millions of years. And that ignores acceleration, deceleration, fuel, shielding, damage, failures, navigation, and the survival of any crew or machine. In science fiction, distance is often solved by faster-than-light travel. But in known physics, faster-than-light travel remains either impossible or deeply speculative. The universe does not provide shortcuts just because we want them. This is why Alpha Centauri matters so much. It is the first test case. If humanity cannot reach Alpha Centauri, then the rest of the galaxy remains a dream seen through telescopes. If humanity can reach Alpha Centauri, even with tiny probes, then perhaps the first wall can be crossed. But crossing the first wall does not mean the entire galaxy opens easily. It only means that one of the hardest achievements in history has become possible once. After that, every further step is still enormous. Interstellar exploration may not be a rapid expansion. It may be a slow, painful, fragile process that unfolds over thousands or millions of years, if it happens at all. This changes the way we should think about alien civilizations too. For decades, scientists and thinkers have asked a famous question: if the galaxy contains so many stars and planets, where is everyone? This is known as the Fermi paradox. The Milky Way has hundreds of billions of stars. Modern astronomy has shown that planets are common. Many stars have worlds orbiting them. Some of those worlds may be rocky. Some may orbit in habitable zones. Some may have water. Some may have chemistry suitable for life. If life can arise elsewhere, and if intelligent civilizations can develop, then why have we not seen clear evidence of them? Why has no alien civilization contacted us? Why do we not see starships, probes, megastructures, or unmistakable signals? There are many possible answers. Maybe life itself is rare. Maybe simple life is common, but intelligent life is rare. Maybe intelligent life develops often, but technological civilizations destroy themselves before spreading. Maybe they stop broadcasting. Maybe they use communication methods we cannot detect. Maybe they are intentionally silent. Maybe we are too early. Maybe we are too late. But Alpha Centauri suggests another possibility that is simple and disturbing. Maybe the distances are the answer. Maybe civilizations are separated not because the galaxy is empty, but because the galaxy is too large to cross. Any alien civilization would face the same speed of light, the same rocket equation, the same energy costs, the same radiation, the same dust hazards, the same communication delays, the same problem of keeping machines alive for decades, centuries, or longer. Physics does not become easier because a civilization is older. They may build better engines, stronger materials, more efficient systems, and more powerful lasers, but they still must deal with distance. They still cannot send real-time messages across light years. They still cannot make ordinary trade practical between stars if travel takes generations. They still cannot govern colonies easily when instructions take years to arrive. They still cannot escape the fact that stars are separated by enormous gulfs. Maybe every civilization reaches a point where it looks outward and understands the same thing we are beginning to understand. The stars are visible, but visibility is not access. They can be studied, but not easily reached. They can inspire mythology, science, and longing, but they may remain physically distant forever. Maybe many civilizations build telescopes, listen for signals, send a few probes, and then realize that their home system is the real boundary of their practical existence. Maybe the galaxy is filled with minds that never meet because light itself is too slow and space itself is too large. That picture is lonely, but it may be closer to reality than the bright science fiction image of crowded star lanes and galactic empires. A galaxy may not function like a connected city. It may function like an ocean filled with tiny islands, each island so far from the others that even if fires burn on the shore, no one can cross in time to speak. Civilizations may rise, wander, listen, transmit, wait, and die without ever knowing whether others existed nearby. The silence of the sky may not mean emptiness, it may mean separation. It may mean that the universe has many voices, but the spaces between them are too wide for conversation. This makes the search for life even more important, not less. If we cannot easily meet other civilizations, then even finding evidence of simple life becomes profound. If Proxima b has microbes, if an ocean exists under its red light, if chemistry there has crossed the threshold into biology, then we would know life is not unique to Earth. We might never shake hands with an alien being. We might never visit their world. We might never have a conversation with an intelligent species. But we would know the universe is alive in more than one place. That knowledge alone would change everything. At the same time, if we find nothing nearby, that also matters. If Proxima b is barren, if planets around red dwarfs are stripped of atmospheres, If Alpha Centauri A and B have no Earth-like worlds, then Earth becomes even more precious. Not because life cannot exist elsewhere, but because the nearest possible examples may not be friendly. We may discover that habitable worlds are rare, fragile, and difficult to maintain. We may discover that Earth is not one of many easy homes, but an extraordinary accident of conditions: the right star, the right orbit, the right atmosphere, the right magnetic field, the right chemistry, the right history, the right timing. This is why the dream of escaping Earth is dangerous when misunderstood. Space exploration is valuable. It is one of humanity's greatest expressions of curiosity. But using space as an excuse to neglect Earth is a mistake. Alpha Centauri will not save us from climate change. It will not save us from war. It will not save us from pollution, resource collapse, or social breakdown. No matter how interesting Proxima b may be, it is not a practical backup planet for humanity. It is too far away. The distance is too large. The cost is too high. The time is too long. Even if a small group of humans someday reaches another star, billions of people cannot simply relocate there when Earth becomes difficult. Earth is not replaceable. That may be the deepest lesson Alpha Centauri teaches us. We often talk about Earth as if it is the starting point of a grand journey, the first stage before humanity moves outward. Maybe, in some long-term sense, that is true. But for now, and perhaps for all practical human history, Earth is the only living world we have. It is the only planet where human beings can stand outside and breathe without machines. The only world with oceans, forests, soil, animals, rain, rivers, seasons, and a biosphere that naturally supports us. Every human life has happened here. Every language was born here. Every story, every prayer, every song, every discovery, every telescope, every rocket, every dream of Alpha Centauri began on this planet. When we look at the nearest star and realize how unreachable it is, we should not feel only disappointment. We should feel responsibility. Because if we cannot easily leave, then we must learn to stay wisely. If Earth is not a disposable platform, but our only true home, then preserving it becomes not just environmental policy, but cosmic common sense. The universe has given us no easy second chance. The nearest star is 25 trillion miles away. Mars is hostile. The Moon is hostile. Space itself is hostile. Earth is the exception. Earth is the miracle. Earth is the place where the universe became aware of itself, through us. That awareness is rare and extraordinary. Most of the universe is silent matter: hydrogen clouds, dust grains, stars, planets, asteroids, radiation, black holes, galaxies. They exist, move, collide, burn, freeze, and evolve according to physical laws, but they do not wonder. They do not ask questions. They do not look up. Here, on Earth, atoms arranged themselves into living cells, then nervous systems, then brains, then minds capable of asking what stars are. Matter became conscious, and that consciousness now looks toward Alpha Centauri and asks whether we can cross the dark. Even if we never reach another star, the fact that we can understand one is already astonishing. We have measured Alpha Centauri's distance. We have studied its orbit. We know it is a triple star system. We know Proxima has planets. We can estimate the ages, masses, and brightness of stars trillions of miles away. We can detect invisible planets by tiny movements in starlight. We can analyze chemical fingerprints carried by photons across years of darkness. We are small, but we are not blind. We are limited, but we are not meaningless. That is the balance this story demands: humility and wonder. We must be humble, because Alpha Centauri shows us our limits. We cannot simply wish ourselves to the stars. We cannot ignore energy requirements, radiation, dust, time, and distance. We cannot assume every dream will become easy because technology improves. But we should also feel wonder, because even from here, we can understand so much. We can imagine missions, we can design probes, we can search for life, we can build instruments that turn faint starlight into knowledge. We can ask questions that no other known species has asked. Maybe someday, humanity will send the first true interstellar probe to Alpha Centauri. Maybe it will be tiny, only a chip attached to a sail, pushed by a laser beam more powerful than anything we have built before. Maybe it will leave Earth orbit, unfold its sail, and accelerate faster than any spacecraft in history. Within minutes or hours, it could reach a velocity that would make current spacecraft look frozen. Then the laser would switch off, and the probe would coast into darkness. No engine roar, no dramatic view, no crew. Just a tiny machine travelling silently through interstellar space with one purpose: reach the nearest star. For 20 years, it would cross the void. It would pass beyond the planets, beyond the Kuiper belt, beyond the sun's familiar influence, into the space between stars. It would endure radiation, cold, dust, and silence. Behind it, the sun would shrink into a bright star. Ahead, Proxima would slowly grow brighter. The probe would not feel loneliness, but we would feel it on its behalf. On Earth, people might forget the mission for years at a time. Children born after launch would grow up hearing that something from Earth was travelling toward another star. Scientists would track it as long as possible. Engineers would hope its systems survived. And then, after 2 decades, the moment would come. The probe would enter the Alpha Centauri system. Proxima Centauri would no longer be just a point of light from Earth's sky. It would be the nearby star, the destination. Instruments would wake and begin gathering data. Cameras would turn toward Proxima b. Maybe the planet would appear as a small crescent, maybe only a few pixels at first. Maybe those pixels would show brightness changes, clouds, ice, or hints of atmosphere. Spectrometers would try to read the planet's light, searching for water vapor, carbon dioxide, methane, oxygen, or other signs of chemical activity. Dust detectors would measure the environment. Magnetometers would study fields. Every second would matter, because the probe would be moving fast. It would not stop. It would fly through the system and continue onward. Then it would transmit. A weak beam of data aimed back toward Earth across more than 4 light years. That signal would travel through darkness for another 4.24 years. On Earth, we would wait. Finally, the data would arrive. Radio dishes or laser receivers would capture a faint whisper from another star. Scientists would decode it, correct errors, reconstruct images, analyze spectra, compare models, and slowly reveal what the probe saw. The first true close-up data from another star system would appear not as fantasy, but as evidence. Imagine the first image. It might not look dramatic to the public at first. It might be blurry, it might be small, it might require explanation. But scientifically, it would be one of the most important images ever created. A world orbiting another star, seen by a machine from Earth. Not inferred, not imagined, not painted by an artist, observed by something that crossed interstellar space. Whether Proxima b is dead or alive, cloudy or airless, icy or scorched, that image would mark a turning point. Humanity would have touched another star system with its instruments. But even that achievement would not make interstellar travel easy. It would not mean humans are ready to go. It would not mean colonies are coming soon. It would not mean the galaxy is open. It would be a beginning, not an ending. A proof that a tiny machine can cross the distance. The next challenge would be larger probes, better communication, improved shielding, and maybe someday deceleration. An orbiter around Proxima would be far harder than a flyby. A lander would be harder still. A human mission would be in another category entirely. The path from first flyby to true settlement could take centuries. And perhaps that is how we should think about the future. Not as sudden expansion, but as deep patience. Humanity may not burst into the stars. It may reach outward slowly, carefully, with long silences between achievements. One probe, then another. One system studied, then another. Each step requiring generations of work. Each success separated by decades. That kind of future is less flashy than science fiction, but maybe more meaningful. It asks us to become a species that can work across time. A species that can plant trees under whose shade it will never sit. A species that can build missions for descendants. That may be the real test of Alpha Centauri. Not whether we can build a fast engine, but whether we can become patient enough to use one wisely. Not whether we can dream, because dreaming is easy. The test is whether we can preserve knowledge, protect Earth, cooperate across borders, invest in long-term science, and accept that the greatest discoveries may not arrive quickly. Alpha Centauri asks humanity to grow up. It asks us to stop confusing speed with progress and start understanding that some goals require civilization-level maturity. There is also a spiritual quality to this realization, even if we describe it scientifically. For most of human history, the stars were symbols, gods, ancestors, omens, navigation points, poetry. Then they became objects of science: suns, plasma, nuclear fusion, gravity, spectra. Now they are becoming possible destinations, but destinations that resist us. Alpha Centauri sits at the boundary between symbol and place. We know enough to understand it physically, but not enough to reach it easily. It remains both real and unreachable, both neighbour and mystery. When you look at the night sky, it is easy to feel that the stars are close because light touches your eyes instantly. A star shines and you see it. But that light has been travelling for years, centuries, or longer before it reaches you. The sky is not immediate, it is layered time. Alpha Centauri's light is 4 years old. Other stars show you older light. Some stars you see may have changed since their light began its journey. Some may no longer exist in the same form. The night sky is a memory field, and Alpha Centauri is one of the freshest memories we receive. Yet even this fresh memory is years old. This should make us feel small, but not worthless. There is a difference. Smallness is a fact. Worthlessness is a conclusion, and it is the wrong one. A human life is tiny compared with stellar time, but within that life exists love, fear, curiosity, thought, and meaning. A civilization may be young compared with Alpha Centauri, but it can still measure Alpha Centauri. A planet may be tiny compared with the galaxy, but it can produce beings capable of understanding galaxies. We are small, but we are the part of the universe that knows it is vast. Maybe that is enough, even if we never become a galactic species. Maybe humanity's purpose is not to conquer the Milky Way. Maybe it is to understand, preserve, and participate in the universe consciously. Maybe sending one probe to Alpha Centauri is not valuable because it begins an empire, but because it is an act of curiosity. Maybe the greatest achievement is not ownership of another star, but the ability to look across the dark and say, "We want to know." Still, the dream of going will not disappear. It is too deeply human. The same impulse that pushed people beyond mountains, across deserts, over oceans, into the sky, and eventually into space, we'll continue looking at Alpha Centauri. Some future generation may decide that the distance is terrible, but not final. They may build the lasers, they may build the sails, they may build fusion engines, they may construct habitats in orbit, mine asteroids, expand through the solar system, and eventually gather enough capability to attempt the first true interstellar mission. If they do, they will not be rejecting Earth, they will be carrying Earth's curiosity outward. But if that future comes, it must come from a living Earth. A dead or broken civilization will not build starships. A species trapped in endless conflict will not cooperate across generations. A planet suffering ecological collapse will not have the stability to reach another star. The dream of Alpha Centauri depends on taking care of home. Exploration and preservation are not opposites, they are connected. The better we protect Earth, the longer humanity survives. The longer humanity survives, the more chances we have to reach outward. The road to the stars begins with responsibility here. So perhaps the final lesson is this. Alpha Centauri is both a destination and a mirror. As a destination, it asks whether we can cross 25 trillion miles of space. As a mirror, it asks what kind of species we must become before we deserve to try. Are we patient enough? Are we wise enough? Are we cooperative enough? Can we think beyond ourselves? Can we build for people who are not born yet? Can we protect the only living world we know while reaching toward worlds we may never touch? Right now, we are not ready. That is not an insult. It is simply true. Our fastest spacecraft would take thousands of years to reach the nearest star. Our societies struggle to plan beyond decades. Our technologies are not yet capable of safe, sustained interstellar travel. Our planet itself needs care. We are at the beginning of the story, not the climax. But beginnings matter. The first time humans measured Alpha Centauri's distance, the universe became larger. The first time we found a planet around Proxima, the nearest star, became more interesting. The first time we send a probe, the boundary between solar system and interstellar space will change forever. For now, Alpha Centauri remains a point of light. In the southern sky, it shines as it has for ages. Ancient people saw it without knowing what it was. Modern science sees it as a triple star system with possible worlds. Future humans may see it as the first interstellar destination. It has been a star of myth, navigation, measurement, and imagination. It may one day become a star of arrival. But until that day, it remains the nearest unreachable place. And that phrase carries the whole story: nearest unreachable place. Close enough to study, too far to visit. Close enough to name, too far to touch. Close enough for light to cross in a few years, too far for our machines to cross in any ordinary human time. Alpha Centauri is not distant in the way other galaxies are distant. It is not remote by cosmic standards, it is nearby. That is what makes it powerful. It shows us that even nearby in the universe can mean impossible. The next time you hear someone say that Alpha Centauri is only 4 light-years away, remember what only hides. It hides 25 trillion miles. It hides thousands of years at current spacecraft speeds. It hides the need for propulsion systems we have not built. It hides radiation, dust, shielding, fuel, navigation, deceleration, communication delays, and psychological survival. It hides the fact that any human journey would either consume a lifetime or require generations. It hides the possibility that reaching the stars may divide humanity rather than unite it. It hides the truth that Earth may be the only world most of humanity will ever have. But also remember what that distance inspires. It inspires better science, better telescopes, better questions. It pushes engineers to imagine new propulsion. It pushes astronomers to search for planets. It pushes philosophers to rethink humanity's place in the cosmos. It pushes all of us to look at Earth differently. The same distance that humbles us also awakens us. It tells us that the universe is vast, but it also tells us that curiosity can cross places our bodies cannot. In the end, Alpha Centauri is not just about space, it is about perspective. It teaches us that the universe is not human-sized. It teaches us that our dreams must confront reality. It teaches us that technology is powerful, but not magical. It teaches us that distance matters. It teaches us that Earth matters. And it teaches us that even if we are small, we are capable of asking enormous questions. Maybe one day, a signal from a human-made probe will arrive from Alpha Centauri. Maybe it will show us a planet under red light. Maybe it will reveal clouds, ice, rocks, or oceans. Maybe it will show signs of life. Maybe it will show nothing but silence. Whatever it shows, that signal will carry more than data. It will carry proof that a species born on one small planet looked at the nearest star and refused to stop wondering. Until then, we remain here, under our sun, looking outward. We remain fragile, ambitious, limited, and curious. We remain tied to Earth, but mentally reaching beyond it. We remain unable to touch Alpha Centauri, but able to understand why it matters. And perhaps that is where all great journeys begin, not with arrival, but with understanding the distance. So the next time you look up at the stars, do not see them only as beautiful lights. See them as real suns, real systems, real possibilities, and real barriers. Somewhere in that sky is Alpha Centauri, our nearest neighbour beyond the sun. It shines close enough to tempt us, far enough to humble us, and brightly enough to remind us that the universe is both more beautiful and more difficult than we ever imagined. This has been Cosmic Depths. If this journey changed the way you think about Alpha Centauri, the stars, and humanity's future, then like this video, subscribe to the channel, and watch the next episode. Because the deeper we look into space, the more we discover that the universe is not only bigger than we thought, it is stranger, colder, more silent, more beautiful, and more terrifying than the human mind was ever prepared to believe. And maybe that is why we keep looking up.